Hi everybody, I'm going to go over SN1 and E1 reactions in this video. So just like we talked about for SN2 and E2, we're really looking at the SN1, the S is substitution, the N is nucleophilic, the E is elimination. So all those things are still the same. The SN1, you're still going to get a substitution reaction. The E1, you're still going to get an elimination reaction and form an alkene. Okay, so the big difference here comes from this unimolecular term. So in SN2 and E2, that's a dimolecular. So the difference there is that the unimolecular means that there's only one molecule involved in the rate determining step. Okay, so when you have your rate determining step, you should only have one compound that has arrows on it. Okay, in the SN2 or the E2, that dimolecular means that you've got two molecules that are interacting in your rate determining step. Okay, and that's either your acid-base reaction or your nucleophilic attack. So that's going to be the main difference here, is that we're looking at a different mechanism for the SN1 E1, but you're ending up with very similar looking products, but not necessarily the same products in each case. Okay. All right. So what do you need for SN1 and E1? You're generally going to be working with weak nucleophiles. So a lot of alcohol, a lot of water. Those are going to be the ones that we use the most. You can use strong nucleophiles and weak bases, so that's things like your sodium cyanide, any of your halides, your acetates, any of those that are a good nucleophile. They've got nice localized electron density, but they are a really stable conjugate base and therefore a weak base. They can do SN1 on tertiary alkyl halides. You're still not going to see them do elimination, but you might see some problems in the book that use those nucleophiles on a tertiary alkyl halide. So then the last thing that we need is we really need a good carbocation. Good carbocations come in a lot of different flavors. Basically, we're looking to avoid anything that's primary and not resonance stabilized. Secondary works okay. Tertiary works better. And then allylic, benzylic are all both going to work well as well. And just make sure that you're careful when you're looking through these, that you don't see an allylic one and say, well, that's a primary carbocation, so I'm never going to care about that. But if it's got resonance, it's going to be more stable than your normal average primary carbocation. So we're really looking for the more stable, the better it's going to be for our reaction. So let's look at an example. We're going to draw out the SN1 and the E1 products and their mechanisms here. So the first step of the mechanism is going to be the same for both SN1 and E1, because we can't do anything without a carbocation. So our very first step is going to be forming that carbocation. And all that means is that we're literally just going to have the bromine leave. Okay, it's taking its electrons with it, and it's gone. Okay, that gets me to this carbocation. I always like to name the carbocations before I do anything else. So this one is secondary, as denoted by the two carbons it's bonded to, but also very importantly, it is benzylic. Okay, so this is a secondary benzylic carbocation. Okay, just kind of naming it helps to give you a bit better of an idea of how stable that carbocation is. This one is quite good because pretty good substitution is being secondary, very good resonance options. Okay, so if we're looking at these, we know that this is a pretty good carbocation, but we always need to make sure that we're taking some time to think about, would a rearrangement occur? Okay, so I always just ask myself, is this going to rearrange? Okay, and we need to get in the habit of asking ourselves this every single time we draw a carbocation, because it doesn't matter what reaction you're dealing with. If you're forming a carbocation, you can have a rearrangement. Okay, so sometimes what is easiest to do is just take this, copy it down here. I'm just gonna do it a little ways down so that we have some space, and then just look at what are the various options that we have for rearrangement. Okay, so if I'm looking over here, I don't have any H's or methyls that I can easily switch. So probably not going to do anything over there. So I guess I don't actually need that much space. But I do have an H here, which I could think about. So let's just draw that out. We'll do that rearrangement, and that's going to get us to this carbocation. So this is actually getting to be a pretty tough guess because this is a tertiary carbocation and this is secondary and benzylic. Okay. So if they are close like that, where you don't have one that's an obvious right answer, it's probably not going to rearrange. Okay. Because if you can't tell very easily the energy difference, that probably means that there isn't much of an energy difference. Okay. So in this case, the secondary benzylic carbocation, not only is it pretty good substitution wise, it's excellent resonance wise. Okay, so that's going to be definitely, I would say probably better than a tertiary carbocation, but that's not something that I'm going to regularly make you try to decide between. And you'll see why I used this particular example. This is not the most clear part for it, but I promise you there is a reason I picked it. Okay, so this, we're going to say not better than secondary benzylic. So this is going to be a no. Okay. Usually they're going to be more obvious than that, though, just to let you know. All right. So next up, we need to actually continue on with our mechanism. So I've got methanol that I'm using here. And just to be clear, that little delta sign is just heat. These reactions are frequently heated. I know that you guys ended up heating a number of yours. This one probably wouldn't need to be heated necessarily, but because it's forming such a good carbocation, but you'll generally see me put it there. Just, it doesn't really matter if you put it there or not, though. I don't care. Okay, so we've got methanol. Keep in mind here that my carbon with the carbocation, that is planar. Okay, so I've got a p orbital that comes up and a p orbital that comes down. So all in all, I can either attack with my nucleophile from the top or attack from the bottom. So that means that I'm going to end up getting two different isomers. Okay, so let's see. We'll do attack from the top over here. And if I come from the top, that means that that's going to be on a wedge. Still have the H, still have the methyl. That's now positive. That other methyl group did not change in any way. Or I can attack from the bottom. Okay, and then attacking from the bottom is going to give me a different isomer. Where now that methanol is going to be on the bottom. Okay, as a dash. Okay, so we're getting closer, but we're not there yet. All right, so at this point, I've got two stereoisomers. Okay, so if we're looking at the relationship here, because I've got this stereocenter, these are diastereomers. So you basically have the potential to be making a mixture of enantiomers or a mixture of diastereomers here, if you have stereocenters. So at this point, we're just going to have methanol come and act as a base. To deprotonate that H on the O, I'm going to shorten this. To get to that product, or my other diastereomer. To get here. Okay, so these are my two SN1 products. Okay, alrighty. Let's look at the E1 products. I'm gonna scooch this down. Oops. Left an H behind. Okay, so the E1 is going to occur from the exact same carbocation. Okay, and again, we're doing the same situation of looking for those beta hydrogens. Okay, so on my left-hand side, I've got a beta carbon, but no hydrogens on that. But on the right-hand side, I do have a beta hydrogen right here. So the difference here between E1 and E2 is I don't have to worry about antiperiplanar in the slightest, okay? The reason I don't have to worry about that is, again, I've got a p orbital that sticks up and down. So if I have an H that's like this, I can do it. If I have an H that's like that, I can do it. But so it does not matter stereo-wise how that's occurring. Of course, because of that, we have extra difficulties in terms of what we're looking at here, because this H can react when it's a wedge, but it can also react when it's a dash. Okay, so we'll look at both of those options. Okay, so my methanol is going to come grab my H. So let me do that in color so that you can see it better. Grab the H and then form the pi bond. And that's going to get me to one E1 product. Okay, but I just as easily could have gone with this conformation. Ooh. Sorry, I have to rotate this in my head a little bit. Okay, so I could have gone here with that H on a dash. And then that would give me this alkene. Okay, so there is no limit on the number of alkenes that you can make here. So each H can actually give you 2 alkenes at this point. So that's definitely something to look forward to. There is a lot less selectivity in SN1 and E1 because there is no stereochemistry requirements here. So originally, if we were doing this in an E2 reaction, we would have only had 1 alkene. But now we've got 2 alkenes just from the 1 proton, okay? So these are the E1 products. And just to have it written down on here, we don't need to care about antiperiplanar here. So all isomers of potential alkenes will be formed. Okay, and that should be a terrifying thought for everybody. Okay, so when we've got this, we've got the 2 SN1 products and we've got 2 E1 products. So generally, your SN1 is going to be the major product. Okay, your book talks about some specific circumstances where E1 is going to be favored. We're not necessarily going to go into that because it gets a little bit granular, I would say. So for this class, we're just going to consider that most of the time our SN1 products, if we can make them, are going to be the major product if we're looking at an E1 or an SN1 type of reaction. We will talk about some E1 reactions where the E1 is like the only product formed, and we'll talk about the circumstances that that occurs in. But that's kind of what we're looking at here for SN1 and E1. We want to make sure that we're thinking about good carbocations, what kind of nucleophile we've got, if you've got an alcohol, that's generally going to indicate that you've got some sort of SN1 or E1 reaction going on here. So let's do one last example. Okay, and we're going to react this with water and some heat. Okay, so first step is always leaving group leaves. Okay, once I've identified that I've got water here, that's going to indicate, like, if anything's going to happen, it's going to be an SN1 or an E1. Okay, so we're going to pop off the leaving group and get to our carbocation. So this is a secondary carbocation. So we need to think about, is rearrangement going to be a possibility here? So again, let's go ahead and take this to a little separate spot. So I can either go with an H over here or an H over here. So let me colors. So if I switch with that one, I'm going from a secondary carbocation to a secondary. And if I do the other side, then I'm getting to a tertiary. So that's going to be what I want to do. So this one is a yes. So we want to use this H, rearrange it, and get to our tertiary carbocation. Okay, so at this point now we're ready for our nucleophile to come in. So we're going to bring in our water, goes and attacks that carbocation. Okay, in this case, if we look at this carefully, I'm not actually forming any stereocenters here. I do have a plane of symmetry if we think about these on wedges and dashes going like forward and back. So I don't actually have any stereochemistry here, so I'm not going to worry about anything in the way of wedge dash at this point, because it doesn't really matter. So then we're going to get that as our SN1 product. That's going to be our major product. And then we have options for E1. Okay, if we go back to our original rearranged carbocation, okay, we can look at, this is the alpha, we've got beta, beta, beta. So in this case, I don't have any bond rotations that are really helpful. So there is no cis trans that I need to worry about here because I can't really twist these, and twisting that is just a methyl twisting around. So my E1 products, let's draw them in here. I'm going to cheat and I'm going to do this with different colors. So we grab the H, form the pi bond, and also do the same thing with the one here. Grab the H, make the pi bond, and then I need one other color. Grab the H, make the pi bond. Okay, and then notice these two are the same. So it's really just the two E1 products that we can make, but these will be minor. Alrighty, so as always, let me know if you have any questions and we will talk about this more in class.